The crystalline universe. Let us imagine our universe as a dynamic crystal, where every physical law is a facet of a hyperdimensional structure that grows through quantum events. The theory of the crystalline vacuum is a further development of the idea of quantum foam, which constitutes the structure of space-time. Therefore, several interesting analogies can be drawn between physical phenomena in crystals and what cosmologists and astrophysicists typically study. Thus, the flow of time in a crystalline universe can be modeled as the process of restructuring a crystal lattice. The characteristic size of each lattice cell is the smallest possible in nature. It has the Planck scale and equals 10 superscript 3m. Electrons are analogous to dislocations, quarks to vacancies in lattice faces, and photons to phonons in crystals. Elementary particles can be viewed as defects in the crystal structure. Black holes become places where the universe's crystal cracks, providing access to other layers. The process of black hole evaporation is analogous to the recrystallization of crystals. Space-time has a discrete structure and exhibits unusual properties due to the geometry of the crystalline universe. The phenomenon of gravity is caused by the effect of crystalline dislocations, and the curvature of space-time is a consequence of stress in the crystal lattice. Dark energy is the result of pressure from new layers growing at the boundaries of our universe. Meanwhile, defects that do not interact with the electromagnetic field would be called dark matter. Quantum memory of events in past universes is recorded in the defects of our crystalline universe, particularly in the spins of electrons. How can we experimentally verify whether the properties of our universe align with those of crystals? It is believed that anomalies in the polarization of the cosmic microwave background, CMB, may be caused by the large-scale structure of the crystalline universe. Quantum vacuum fluctuations are due to the thermal motion of the main structural elements, the atoms of space-time. If our crystalline universe is anisotropic, differences in the speed of light could be detected depending on the direction of propagation relative to the crystal's axis. Moreover, the speed of light would be discrete. Anisotropy would be observed in the distribution of gamma-ray bursts. Gravitational waves would have spectra characteristic of the cracking of the crystalline universe's lattice. The crystalline universe theory proposes, instead of string vibrations and 11 dimensions as in string theory, considering the geometry and motion of crystal defects in 2 spatial and 1 temporal dimension. Dark matter and the crystalline universe theory. According to the crystalline universe theory, the phenomenon of dark matter is caused by defects in the space-time lattice that create stress. These stresses manifest as gravitational effects in the absence of particles and, consequently, mass. This also explains why dark matter never collides with itself, because defects are not particles but the absence of particles. Dark matter should form thread-like structures along the anisotropy axis of the crystalline universe. This aligns with observations of filaments in the large-scale structure. Dark matter halos must be elongated along the anisotropy axis of the crystalline universe. The distribution of dark matter must correlate with the anisotropy of the cosmic microwave background radiation. Additionally, defects in the space-time lattice have their own sound modes, which can be studied at the resonant frequencies of gravitational waves. What could be the main principles of crystalline cosmology? The overall macrostructure of the universe would more closely resemble a fractal dendrite. Galactic filaments would form along the edges of the crystal lattice, while voids, the vast empty regions, would be analogous to gaps between crystal faces. Such a crystal would be anisotropic, meaning the distribution of matter in the crystalline universe would follow certain geometric patterns, such as octahedral symmetry. At the boundary of the observable universe, new layers of space-time would form, akin to crystal growth in a supersaturated solution. Possible evidence for this includes anomalies in the distribution of quasars. The speed of light propagation would depend on direction, as the crystalline universe would be anisotropic. New epochs of the crystalline universe would resemble phase transitions. The Big Bang would be analogous to the formation of a crystal nucleus. Inflation rapid crystal growth. The modern epoch, slow recrystallization with the formation of defects, namely black holes. The event horizons of black holes are analogous to dislocation boundaries, and Hawking radiation is one way of relieving stress. The death of our crystalline universe would occur when it becomes a perfect monocrystal. An alternative would be infinite polycrystallization. The crystalline universe would be just as beautiful as our own. An observer with a telescope would see galaxies aligned along predicted geometric lines, while intergalactic voids would have distinct facets. The spectrum of light from distant sources would depend on the observation angle. Actual observations. The anisotropy of the cosmic microwave background, CMB, could be interpreted as traces of the crystalline universe's facets. Evidence supporting the crystalline universe theory includes the quadrupole asymmetry of the CMB and the pattern of higher multipole moments on the CMB map, resembling the projection of crystal facets. Interestingly, the direction of anomaly axes strangely coincides with the plane of the solar system, ruling out systematic errors. The distribution of gamma-ray bursts, the most powerful explosions in the universe, exhibits statistical anisotropy, specifically dipole asymmetry. This was discovered while studying several thousand gamma-ray bursts and may indicate the presence of certain axes in the crystalline universe. A correlation in the polarization of light from quasars has been detected across scales of 1 billion light-years. This can be explained by the crystalline properties of our universe, as it resembles the birefringence effect in crystals. The Hubble constant has different values depending on the observation direction. Studies indicate that our universe expands differently in different directions, with a 3% variation. This discrepancy may point to anisotropy. An anisotropic universe would have polarization modes of gravitational waves distinct from the standard ones. Future instruments like the LISA and Einstein telescope detectors may detect them. It is important to note that effects indicating universe anisotropy are extremely small and difficult to measure. Even if experimental data suggest anisotropy, it can often be explained by other means. The upcoming LightBird mission, set to launch in 2028, will measure the polarization of the CMB with an accuracy of 0.1 degrees. Analysis of JWST data may help detect anisotropy in the distribution of the earliest galaxies, if it exists. If the anisotropy axes of our universe exist, we should find them within 10 to 15 years. Even a negative result would transform our understanding of space-time.
FutureMind. Imagine the future